we have been looking at a generic skeletal reaction mechanism, skeletal because we are only looking at intermediates being present here. We are oblivious to the presence of the other stable species, reactants or products, except of course saying that we start with some stable species and you would end with some stable species. This need not be the same as that. So this is like a gas phase termination, this is a surface termination. We want to distinguish between these, and we want to notice that this is a chain propagation step, this is a chain branching step if alpha is greater than 1, and ultimately we now write a rate equation for the concentration of the intermediate as this, where F's actually are essentially factors on the reaction rate constants, because these are not, this is only skeletal. So this F's are the ones that represent the rate constants, then we apply the steady state approximation and get a expression for the concentration of the radicals intermediates, with which we now try to plug in the expression for the rate of production of the final product, and we get this expression, right. So what we mean by a chemical explosion is when your dCp over dt goes to infinity, and that happens when the denominator goes to 0, and the denominator can go to 0 only when alpha is greater than 1, and alpha greater than 1 indicates a chain branching situation. That means you now have a creation of radicals, more radicals in the second step, right. So this is what we have seen so far. The additional thing that we have also begun to notice so far is, question is what happens as you now change the pressure, right. So as you change the pressure, we expect that the surface termination should actually try to come down, because the molecules are busy colliding among themselves rather than colliding on a surface. Okay, the surface location is fixed, its surface area is fixed, whereas the molecules are actually trying to collide with each other as you increase the pressure more than they actually collide with the surface. The same molecules, the probability of collision among themselves is more when compared to collision with a surface. Therefore the surface termination is actually going to decline as you increase in pressure. So if you were to now try to plot how this is going to happen, so let us suppose that you plot your various F's that are participating in this equation with pressure. So let's now say we have a pressure showing up. We expect that Fs should decline like this, and on the other hand, for a similar reason, Fg should actually start increasing as you increase in pressure, because you now have to have more and more gas phase termination happen as the pressure increases, relatively speaking. Therefore you're now going to have a curve for Fg that goes like this. Now put these two, I'm sorry, should have looked at so you need to have the gas phase go up like this. In fact, there is no reason to believe it would actually ever flatten out, because as you keep on increasing the pressure, the Fg should keep on increasing pretty much nonlinearly, and therefore we now expect the Fg to go like this. And then we are now looking at Fs and Fg together, you see, because they are termination reactions. Therefore your Fs plus Fg is now going to go like that. So as you increase in pressure initially, Fs comes down, and therefore Fs plus Fg comes down, but as you increase in pressure further, Fg grows up even though Fs comes down, and that makes up for it, and therefore the Fs plus Fg keeps increasing further. Now this together is now balanced by the Fb alpha minus 1, right. So the question is, how does that go? And we expect that you now have to have a production of intermediates because of chain branching, and that need not necessarily grow with pressure forever, right. So that means we expect that this should actually go more like that, right. So this is now Fb alpha minus 1. That means as you keep on increasing the pressure, the chain branching need not happen forever, so it begins to level off after a point. But the interesting thing here is the question is, when is this matching this, right? And graphically we can now see that Fs plus Fg now is having the same value as Fb times alpha minus 1 here and here. So there are two pressures at which you now have this match happening that corresponds to the denominator going to 0, which corresponds to the rate of production of products just exploding, right. So if you were to now look at how the dCp over dt is going to fare with pressure, right, we now try to say, let us just bring this down, right. So strictly speaking I need only 1/2 of the positive domain, so I could draw a axis somewhere up there, allowing for some space at the bottom as well, because we are looking at net production of products which could go negative. So what this means is we are now looking for some production of products that starts from somewhere, we don't know exactly where to start, let us say some pressure, low pressure, and then it goes up to infinity, right. And in between here you now start with a negative infinity, because the denominator is now beginning to flip sign, okay. So you are now having if you now go here, you now have Fb times alpha minus 1 greater than Fs plus Fg. So you just had a flipping of signs, so it starts from negative infinity, goes all the way up, and then comes back to negative infinity again, and you now have a flipping of signs again, right. So what is going on? We are now saying that at low pressures you have a significant surface termination, and then there is some point as you now keep on increasing pressure that the intermediates are beginning to actually get produced by chain branching much more than the rate of termination, okay, because the termination is actually coming down as you increase in pressure. So you are producing more and more intermediates and creating an explosion. And the other time, so and then you now get into a explosive regime, and you know that the other time you are now going to have an explosion is when the reverse happens. That means you now have a lot more gas phase termination, right, and so the gas phase termination keeps increasing, but the production is not increasing that much, okay. So this is now tapering off, and then you now have a reversal again of Fs plus Fg exceeding Fb times alpha minus 1. So these two pressures now are, we are looking at pressures essentially, right. That means we haven't really bothered about what we are doing with temperatures, okay. So the reason why we are doing that is because with pressures we can think about collisions increasing or decreasing, or surface termination declining in importance relative to gas phase termination, and so on. All these things are pressure related. We haven't thought about temperature, so it's as if like we have kind of fixed the temperature, okay. So the corresponding picture, if you were to now bring in temperature here and pressure were to be plotted over there, okay, would be to now look for a curve that would go like an inverse S, where you were to fix your temperature at some point, at any point, okay, and then you will find that this is your, let us suppose that this is your P1 and this would be your P1, okay, and then you have a P2 here, then this is your P2. That means for a given T, this mechanism is able to, this mechanism is able to show that there would be what is called as two explosion limits. So you have a explosion regime here and no explosion on this side, or in other words in the PT plane, this line marks a boundary which corresponds to crossing over to explosion, alright. That is to say, if I were to fix my temperature and keep going up in pressure, that is like saying go horizontally in this direction, I now cross an explosion point and get into an explosive region until I get to P2 when the gas phase termination begins to predominate over the chain branching, and therefore I cross into the no explosion limit, alright. And this obviously can actually move back and forth as you change the temperature. Yes, please.
So at the explosion, that rate of production must go to infinity now, sir.
Yeah.
So there you have written tends to 0.
I'm sorry. Thank you. Was there a cause of confusion for about 20 minutes? We should have remedied it long ago, right? So okay, so we now can explain this, right? So this is the famous S curve, although it's an inverted S, but it's okay. We will just call it an S curve. We always name things based on what we're familiar with. So then the question arises, hey, the S curve also has another point, P3. That's not explained by this one here, okay. So how did we get the S curve? This is an experimental observation. That means you now take, what is this P and T that we are looking at? Those are the initial pressure and temperature. So you now take a reactant mixture at a particular pressure and temperature, okay. If it were to be located somewhere here, that means it's not going to explode, chemically explode. But if you were to take a chemical mixture and get it up to a certain pressure and temperature that would locate itself somewhere here, that means it's going to go through a chemical explosion, alright. That's what it really means. Or you could take a chemical mixture and then keep it over here, your dCp by dt is not going to be infinity, and then keep on increasing your pressure, and then you're going to go through an explosion as you now cross that curve, that limit. And if you now keep doing this experiment, you will find that this you get this curve for different temperatures. You do this and you get this curve, and the curve is actually an inverse S shape, whereas what we have done so far can explain only about two pressures to two limits, okay. It doesn't explain the third limit that is also observed, okay. So how are we explain the two limits? It's essentially looking at chain branching versus a surface termination, or chain branching versus a gas phase termination, okay.
The state of the mixture is at the line at that S curve, inverted S curve. What will happen? It will
then you have to look at then you go a little bit further. You have to look at stability. So what we have done is only to look at the equilibrium, okay. So you have to perturb, and then you will find that if you're here, then you I don't want to get into this. So strictly speaking, if you're like into stability, you will draw like a dotted line for this and a solid line for this, and so on. So the solid line indicating that it is stable at that point, whereas the dotted line indicates it's unstable, okay. So unstable or stable really means that depending upon which way you perturbed, okay, you perturbed into the no explosion side, it will not explode, but if you perturbed in the explosion side, it will continue to explode, and so on. That is if it's unstable, and so on. So let's not get into that. That's getting further out, okay. So fine, we'll just keep it that way. The question then is, what about the third limit, right? There are quite a few explanations for this. One of the explanations that I would like to, in fact, this is observed for, let's say, the H2O2 system, right? Observed for okay. So S curve as observed for the H2O2 system. So the question is about the third limit. There are a couple of 2 or 3 theories about this. all of this actually coacting with each other. One of the things that we have been talking about when we are talking about changing pressure is the competition between unimolecular to bimolecular reactions or bimolecular to termolecular reactions. So when you are now looking at very high pressures, then the termolecular reactions become very important. Okay. So the question then is, you now look at the scheme that we already had depicted earlier for H2O2 system, a basic 9-step reaction scheme, okay, where you now have a termolecular reaction step. So this is now going to give rise to a new intermediate, as opposed to OH and OH alone. You now have a HO2 that also has a surface termination and a gas phase termination, you see. So the termolecular reaction giving rise to a new intermediate is one of the mechanisms that explains a very high pressure limit. This is one idea. The second idea is you now also get into a H2O2 cycle. That means at this time we are not really bothered about the formation of hydrogen peroxide, right. So there is we find a third limit in the experiments, right. So this is due to importance of termolecular reactions at very high pressures. So the production of HO2 is a hydroperoxy radical. So at very high pressures you now have the importance of production of hydroperoxy radical. And the second idea here is we need to consider reactions involving H2O2 as well. So example, I'm saying example because this is not exhaustive, okay. As a matter of fact, we have about 9 reactions here. In reality you might have to consider something like 40 reactions and maybe 9 species, okay. So the 9 species here would be like H2O2 HOOH did I say H2O2 HOOH H2O HO2 H2O2 O3, okay. So we may have to consider as many as 9 species and about 40 reactions, but the idea basically is what is the least number of reactions and species that we need to consider to explain a certain phenomenon. That is the way we would approach chemical kinetics all the time, alright. So that is a reduced mechanism that we need to adopt. So here for consideration of H2O2 we may have to say, let us say we now have HO2 plus HO2, that is 2 HO2 gives H2O2 plus O2, HO2 plus H2 gives H2O2 plus H, H2O2 plus OH gives H2O plus HO2, H2O2 plus H gives H2O plus OH, H2O2 plus H gives HO2 plus H2, and H2O2 plus M, that is a gas phase termination, gives 2OH plus M. You see there are a couple of things that I would like to point out with a new intermediate that could be formed. First of all, if you want to look at what happened to the HO2 in this reaction step, we now said HO2 is getting produced by this termolecular reaction that would be pretty important at high pressures, number one. Second thing, how does it get absorbed? It has a surface termination and it has a gas phase termination. The gas phase termination is HO2 plus H2, which is the stable reactant, produces a stable product water plus OH. But there is an alternative path, right? So you could now say HO2 plus H2 produces H2O2 plus H. Alright, now this is another chain branching, right, and it now produces a new intermediate H2O2, which could now get consumed in a succession of steps. And notice that this, for example, is a reverse of that. Okay, so as H2O2 is being produced, it could equilibrate with its consumption in a reverse reaction, right? So you could have a second set of intermediate production that is possible here as a secondary route to a termination of a particular intermediate at high pressures. And of course the last possibility that's termed is thermal, that is it's not really a chemical explosion, so not necessarily just a chemical explosion. The third thing is the third limit could be thermal in nature, that is to say reaction rates are shoot up so high and these reactions are exothermic, keep in mind. So when you now have exothermic reactions that are happening very fast, right, then you have a huge rate of generation of heat, right, that could actually increase the temperature, and as the temperature increases the reaction rates increase further, right, and as the reaction rates increase further the heat release rate increases further as well, and so on, right. So that's what's called as a thermal runaway. And so under these conditions, the steady state approximation is not valid. In other words, you couldn't hope to explain the third limit particularly within the framework of a steady state approximation. Okay, so you have to account for the thermal runaway in explaining the third limit. So effectively we are saying essentially that a mechanism like this is essentially taking care of like one kind of intermediate. If you now have multiple intermediates, you might have other limits as seen in a H2O2 skeletal mechanism plus a additional possibility of H2O2 formation. Keep in mind another aspect is the thermomolecular versus bimolecular, which becomes important at high pressures. So these are the things that actually constitute the third limit is what we can say from here. The next thing that we want to now say when we are now beginning to talk about thermal is where do we go from here. So let us now look at the possibility of combining chemical and thermal processes right. In the very first class we talked about combustion is having convection and diffusion and chemical reaction. Okay. convection is about the flow, diffusion is about mixing of species, and then you have the chemical reactions anyway. And of course we said that we are essentially looking at typically fast chemical reactions, right. When we said fast, we are essentially looking at the chemical kinetics. So this is something that we did after we did the chemical equilibrium that would give you the adiabatic flame temperature. So we've done chemical equilibrium, all right, and then we have done chemical kinetics. The chemical equilibrium gives you what the adiabatic flame temperature should be for the final products, assuming that they exist in equilibrium. Chemical kinetics basically tells you what happens to the rates of reactions when they now depart from equilibrium end states. That means you start from reactants and then now you want to proceed towards products. What's the rate at which you are now going to go from here to there, right, as you now depart from an equilibrium initial state and proceed towards a equilibrium final state. You are now departing from this equilibrium and going towards another equilibrium, right. All along when we are doing chemical kinetics, we are not really worried about changing temperatures. We are saying that a reaction rate is equal to a rate constant times concentrations raised to their stoichiometric proportions, and the concentrations will depend on pressure, but the rate constant is the one that will depend on temperature in an exponential fashion, right. So if I were to now look at a system of reactions where multiple species are involved and I want to actually keep track of rate of production of a particular species in all the reactions put together, it could be getting produced in one reaction, getting consumed in another reaction. I now have to sum over all the rates of production of that particular species in each of those reactions across all the reactions, and then I have to keep track of what's the rate constant for each of those reactions times the products of the concentration in those reactions raised to their respective stoichiometric coefficients and so on. And in all these things I now get a system of ODEs, right, which are for each of those concentrations the rate of production of those species concentrations, right, dCi over dt. And then what we did was, well, we say ODEs are very nonlinear. You have an initial value problem, all right, but you have to now solve these things simultaneously. These are stiff equations because you now have very small chemical times that you have to take care of and so on. Therefore we said if you apply a steady state approximation, you could now set a bunch of dCi over dt's equal to 0 because all of them are intermediates, and keep track of only the stable species reaction rates or production rates. Another way was a partial equilibrium approach, where we said that those reactions that are involving intermediates could be assumed to exist in equilibrium with each other because they are happening very fast when compared to the final step, right. Thereby we now say we can replace the ODEs for those species by algebraic equations through their equilibrium constants. So these are things that we would try to play with under different conditions to simplify our equation set, all along not bothering about what happens to the temperature. In other words, if you now have a set of reactions that are happening, they would give out heat and take out heat, okay. We never really bothered about it, and we didn't worry about what is the net heat that is produced in this set of reactions. And while you're doing combustion, we're expecting heat out as a net thing. There are some reactions that are going to take away heat because they're endothermic, but largely we're expecting that many reactions are going to put out heat, right. So when you're in high school, you write these simple reactions and then you put a delta H at the end, okay. We never did that when we did chemical kinetics. We did that when we were doing thermodynamics, then we dropped that habit because we are now looking at how fast we want to go. We didn't worry about what's the heat that's going to come, right. Now what's the problem? Why should we have worried about it? Can't we just worry about the rates alone? Should we worry about the heats along that come along? The answer is, when the heat is going to come along, it's going to heat up the place, and when it heats up the place, the temperature is going to change. The temperature changes, the reaction rates are going to change. right, and the reaction rates are going to change, the heat release is going to change, and the temperature is going to change, and so on. So the real problem is in taking into account not only the chemical kinetics but also the changes in temperature because of the heat release that happens in these chemical reactions, right. This is still not bothering about the flow and mixing. We are still not really looking at a full blown combustion problem, but we go take baby steps. We do equilibrium, we do depart from equilibrium and look at how fast, then we start worrying about what's happening to the heat that comes along and the changes in temperature that will influence the how fast thing again, right. So that's the next step that we want to do. So here we neglect mixing, right. Whenever you neglect something, it doesn't mean that it doesn't exist, okay. You're taking it for granted, right. So that's what you do with your parents and teachers, huh? you neglect them not because they don't exist, right. You just take them for granted. So here again what you're doing here is we are saying that it's all perfect, everything is fine, no problem, my parents always love me, so what's the problem, huh? So it's like we assume perfect mixing all the time. That is again to further elaborate, we say uniform instantaneous mixing, right. Uniform to cover space and instantaneous to cover time. That means at all times and in all places you expect mixing to happen uniformly, therefore any species that is there everywhere instantaneously, okay. So if you now have a mixture of species, reactants, products, intermediates, all of them get mixed instantaneously everywhere in the region that we are interested in. This is what we are basically assuming, right. That means you don't worry about spatial concentration gradients, and this is going to become very important when we start thinking about mixing in greater detail, okay. Spatial gradients in concentration are the ones that are going to drive mixing. We now suppose that you have a spatial uniformity all the time. That means if you now have a change in the concentration that leads to a instantaneous mixing, so that the concentration is uniformly spread in space, so that you don't have any spatial concentration gradients that will drive the mixing, okay. Is it okay? Is it okay to do this? Well, there are conditions under which this will be very useful for us to think about, okay. So for example what we are basically saying is the mixing has to be so fast, right. Now typically mixing is not really as fast as chemical reactions when you're now looking at combustion kind of chemical reactions, right. So how doesn't make sense? Well, why don't I take my hand and put in there and then start mixing as vigorously as I can? Yeah, sure, yes. Of course don't do this because you're going to get your hands burnt, okay. You can put a spoon and start stirring, right. So this is very typical. I mean what you're talking about now is to promote mixing through things like turbulence, okay. So if you now have like a highly turbulent situation, okay, where the turbulent mixing is going to promote a homogenization of this mixture, okay, instantaneously, then we take advantage of that, and we think that turbulent combustion is very complicated, but there are regimes of turbulent combustion which we could take advantage of. There is like so much turbulence in there that it just smears out everything, and then the mixing is complete. We don't have to worry about it, right. So that's a kind of approximation that we could apply to many practical systems as we will see, right. So we can also in many situations we can also neglect the details of the flow that means you either don't have a significant flow at all to talk about, okay, in relation to what we are thinking about, that is chemistry and temperature gradients and so on, or the flow is so complicated that we don't want to worry about the details. Okay, it's always like it's either like you don't have, when you say you neglect mixing, that could have been fine when you didn't have any mixing to worry about, but what we are basically saying is there is a lot of mixing that's going on that we don't have to worry about it. Okay, similarly when we say we can neglect details of the flow, then that means either you don't have too much flow, okay, that's good, or you have so much flow that's going around that it's very difficult for you. So what do you mean by so much flow? Turbulent flow, right. So when you now say turbulent mixing, it's basically caused by a flow. Turbulence is essentially a fluid dynamic situation. The mixing that comes with it is accompanying the turbulence, right. So in a sense when you're now trying to put these two together, they go together, the assumptions basically kind of go together. If you're thinking about a intense turbulent combustion situation, then the flow field is so complicated that we don't want to worry about it, okay, it neglect its details, and it also facilitates a more instantaneous mixing that we don't have to worry about it, okay. So sometimes we could admit a simple description of the flow in a way that does not really affect our focus on looking at the coupling between chemical and thermal reactions, the thermal processes, right, chemical reactions and the heat. So essentially we are looking at we are now taking a magnifying glass and looking at only a coupling between two things, the chemical reactions and the thermal field that it creates, okay. Anything else that comes around is something that we want to neglect and look for situations when we can neglect it, right. So if you can allow for a simple description of a flow in some conditions, some situations, right, that does not really come in the way of our looking at this combination, then we could admit it, right. So let's just look at when are those conditions that are possible, right. So the balance here, so the balance to be considered here is between production or consumption of species in chemical reactions and the thermal energy associated with it, right. Obviously we want to do this in a region that is that's meaningfully, when you now say you want to have instantaneous mixing, it's possible only in a small region, right. So we would now want to confine our attention to in a region, okay, in a region such as a a reactor. So typically a reactor is a terminology that is used by chemical engineering people. The aerospace people call it a combustor, okay, but essentially the chemical engineering people are looking at like a broader set of chemical reactions that are possible than just combustion kind of reactions. So they would call a region where they want to have chemical reactions happen as a reactor, okay, and then we are looking at a intense mixing happening in a region that we want to call a reactor. Okay, so what are the typical kinds of reactors that we want to look at that will facilitate handling this restricted set of conditions is a question. Broadly we could say we can say reactors are like fixed mass, reactors or open flow. Alright, that means you are now taking a certain mass of reactants, allowing for the reaction to happen, and the reactants now become products, but the mass does not change, right. Mass is conserved in a chemical reaction anyway, therefore the mass of the products should be the same as the mass of the reactants, or the mass of the system that we are talking about should remain the same through the reaction, right. So this is now looking at a fixed mass system. On the other hand, you could have open reactors, that means you now have an inlet and an outlet, yeah. So you now have reactants come in this way, go through some reactions and get out as products. So it is sort of like a open system, right, and it is a open flow system, right. So you can't really talk about a fixed mass, you might be able to talk about a fixed mass flux or a mass flow rate, right. When you now talk about a fixed mass flow rate, that means implicitly you are thinking like a steady state. So on a steady state basis, if I now keep in a flux of reactants come in this way, a flux of products go out that way, and there is like a intermediates that are formed and get quenched by the time you have the products that go out, right. All of this is happening all the time. So that is like a steady state situation. As opposed to that, a fixed mass reactor is like a batch process, where you now take a certain mass of reactants and you have to allow for things to change in time from a set of reactants to set of products, right. Obviously that is not steady state, things change in time, okay. So we are essentially looking at fixed mass systems, right. We look for a set of ODEs, right, in time for chemical composition and temperature, okay. Previously when we were worried only about chemical kinetics, as if the temperature was fixed artificially by us externally, that is possible. You could actually have a chemical reactions happening in a bath that is maintained externally by a constant temperature, right. That is what we were thinking earlier on for a physical system, okay. But here, in addition to the chemical composition, so when you say composition, we are now talking about, let's fix it, we are now talking about molar concentration, Ci, for the ith species, I going from 1 to n for n species, right. So in addition to the concentrations, molar concentrations of chemical species that will give the chemical composition as a function of time, we also have to track the temperature as a function of time. That means you need to have a ordinary differential equation in time for temperature as well, that is like d capital T over d small t. Okay, there must be a rate equation of sort for the temperature change in time. Okay, given initial conditions in these, right. So this would actually be a initial value problem. What you will find is the rate of production, net rate of production of each of the species whose composition, whose concentrations that we are interested in will depend on the concentrations of lots of other species and temperature. And similarly, the rate of change of temperature, the equation that we write for the rate of change of temperature with time, will involve the rate of production of other species, which in turn means that it will involve the concentrations of other the species. So you are now looking at a coupled set of ODEs. Okay, that is, each equation in the set has variables that are present in most of the equations. That means you have to solve all the equations simultaneously. Okay, so that is one initial value problem for the entire simultaneous set of equations. On the other hand, if you now look at open flow systems, we assume them to be steady. That means we just say let's not worry about unsteadiness. That means we don't worry about evolution of the concentrations from reactants to products, okay, in time, and correspondingly the temperature that's also associated with it. Okay, that means we don't have to have ODEs. We could simply look for algebraic set of equations, or in a crude sense, we will look at the details a lot more carefully as we go along, but in a crude sense it's essentially saying let's now throw away terms that involve d by dt, okay, or any change in anything with respect to temperature with time, let's get rid of it. You now set it equal to 0 at steady state, then a ODE with the first derivative, a first order ODE with the first derivative thrown in, you don't have any differential equation anymore, right. So effectively you could reduce your system of equations to a simultaneous algebraic set of equations, right. So we could get a algebraic set of equations, I should say set of algebraic equations, in concentrations and temperature, right. Okay, why am I saying we could is if you do not consider any spatial variation. Okay, now what we looked for avoiding earlier is a spatial variation in spatial gradients in concentration. If you assume that spatial gradients in concentration don't exist, but let us suppose that you now have a duct that could be a convergent divergent nozzle where reactions are happening, like for example at the towards the exhaust of rockets. Okay, so when you now have chemical reactions that are happening in a combustion chamber and pushing into a convergent divergent duct, you have a flow. So if it is possible for you to have a simple description of the flow, and the flow changes as we go along because of the convergence and divergence and so on, that's going to distribute your temperature and species in a convective manner, not in a diffusive manner. Okay, diffusive is what we are trying to avoid in our formulation, but you could look at a variation in space purely because of convection by admitting a simple description of the flow. So, or we could get ODEs again, but this is not ODEs in time but ODEs in space, okay. So ODEs in space, in 1D space, that is the reason why it is ODEs space for concentration and temperature, concentrations and temperature, by admitting a simple, let's say quasi 1D flow description. Alright. So it is possible for us to actually try to do a few different things within this framework effectively, okay, and we will now for many of these different conditions we will now be able to get a ODEs in time or ODEs in space or algebraic equations which are simply taking into account only the chemical reactions, the mass production of species or mass depletion of species, and the heat release that is associated with them, doing an energy balance of that, okay. We'll continue from here on Monday.